For the last century, the whole concept of getting energy for your vehicle has been, well, it's been anchored in this very fixed, very physical reality.
Yeah, a completely immovable one.
Exactly. Picture a gas station. It's that glowing canopy on the side of a dark highway. It's concrete. It has underground tanks. It is totally permanent. You have to go to the energy.
Right, we basically structured our entire transportation geography around that one assumption.
Yeah.
The vehicle must travel to the fuel. It's a destination-based model that we've just universally accepted as, a permanent fact of life.
But today we are going to completely reframe that concept for you. We are asking what happens when the energy actually comes to you.
Which changes everything.
It really does. So whether you are an EV owner who dreads that moment the battery gauge turns red, or you're just someone tracking the shifting infrastructure of our cities, the way we power our lives is fundamentally changing.
It is.
Because there is a sprawling, mostly invisible collision happening right now.
Well,
And it's between our aging, centralized electrical grid and the absolutely booming electric vehicle market.
right. And bridging that collision is a rapidly growing industry called charging as a service, or CARS.
Right.
It relies on mobile charging technology. And it sounds like a very niche tech solution on the surface, but is actually rewiring the entire convenience economy.
To understand how this works, we've got a really fascinating stack of research for this deep dive. We are looking at historical reports on the U.S. power grid from Contrary Research.
Highly detailed stuff.
Yeah, it's great. And then we have some heavy engineering analysis from a journal called JOR. They look at what they call mobile electric charging vehicles, or MECVs.
Right.
Plus, we have market analysis from TechSci and Benzinga looking at industry innovators like B-Charged EV and Spark Charge.
Yep.
And we'll tie it all together with some really revealing consumer behavior data from Recharged and TGM research.
To really grasp this mobile charging boom,
Yeah.
practically impossible to understand it without first looking at the architecture of the grid itself.
Yeah, we have to start at the root of the problem.
Exactly.
Yeah.
Because the mobile solution only makes sense once you realize that our current fixed infrastructure is essentially buckling under the weight of modern demand.
Right. The grid was built on a century-old model. It goes all the way back to the war of currents between Edison and Tesla. Tesla's alternating current won out because it could travel long distances, right?
Right.
So we built this system of pushing current in one direction, from a central hub, like a massive coal or hydro plant, way out to the consumer.
Which was a brilliant design,
Yeah.
for the 1920s.
Right. But the Contrary Research report points out just how outdated that physical hardware is today. I mean, about 70% of transmission lines in the U.S. are over 25 years old.
Yeah, they have far exceeded their intended design life.
They are essentially antiques at this point.
And look at what we are actually demanding from that aging metal right now.
Yeah.
In 2022, the U.S. used a staggering 4.05 trillion kilowatt hours of electricity.
Oh, wow.
Yeah, that is 14 times the level we used in 1950. The physical wires out there are operating near their absolute thermal limits.
And now we're plugging cars into it.
Yep, millions of them.
By 2030, they estimate EVs alone could draw nearly 5% of all U.S. electricity output. Okay, let's unpack this for a second, because we are essentially trying to run a modern AI data center on a dial-up internet connection.
That's a great way to put it, actually.
Right. The grid was built as a one-way street for very predictable traffic. Now we have millions of power-hungry EVs demanding massive amounts of energy at random times and in random locations.
Which is dangerous because it forces a centralized, highly rigid machine to behave like a distributed dynamic network.
Yeah.
And the result of that is severe fragility. I mean, we saw the cracks start with the 1965 Northeast blackout.
Oh, sure.
And more recently, we saw the catastrophic grid collapse in Texas in 2021.
Mm-hmm.
The system just doesn't have the slack it used to have.
So you'd think the obvious solution is just to, build more power lines and install more fixed charging stations.
Just pour more concrete, right?
Exactly. But the regulatory reality of doing that is an absolute nightmare. There is an unprecedented interconnection backlog right now.
Yeah, it's massive.
As of late 2023, there were 2,600 gigawatts of proposed generation and storage projects just sitting in queues, waiting for permission to literally just connect to the U.S. grids.
And just to put that 2,600 gigawatts in perspective, that is double the current installed capacity of the entire country.
Wait, double?
Double. Sitting in a waiting room, basically.
Yeah.
And more than 70% of those proposed projects in the queues never even get built.
Wait, hold on. 70% just drop out. Why?
Yeah.
I mean, if the demand is there, what is killing all these projects?
It almost always comes down to utility grid studies and cost allocation.
Okay.
So when a company wants to build a massive fixed EV charging hub, the local utility has to run a study to see whether that new load will just, melt the neighborhood
Right,
transformers.
which makes
It
sense.
does. But if the study says the local substation needs a $50 million upgrade just to handle your chargers,
Right.
the developers usually ask to foot that bill.
Oh, wow. So they just walk away.
Exactly. They abandon the project. If you want to deploy a fixed EV charging solution right now, you are looking at 18 to 24 months just to get through the utility delays, the permits, and the construction.
So we have an explosive adoption of EVs layered on top of a fragile grid.
Right.
And it's totally bottlenecked by a 2-year delay just to plug a new fixed charger into that system.
Exactly. And that macro problem creates a very real and, honestly, highly stressful micro problem for you out on the road.
Yeah.
Because the fixed charger deployment is so sluggish, the ratio of electric vehicles to public charging ports in the U.S. is currently sitting at 29 to 1.
Oh, man. 29 to 1, that is a severe bottleneck.
It is. And that 29 to 1 ratio assumes the port actually works when you get there.
Right, which is a big assumption.
Huge. The data shows that 25 to 50% of public chargers might be offline, broken, or just blocked by another car when you pull up.
Which feeds right into the dominant cultural fear about EVs, right? The terrifying idea that you're going to run out of battery in the middle of a desert highway and just be stranded.
The classic range anxiety.
Exactly. But the data we have from Recharged completely flips the script on what is actually stranding these drivers.
Yeah, the recharge data is fascinating because according to their recent roadside assistance metrics, only about 1 to 2% of EV breakdowns are actually caused by the high-voltage main battery running completely flat.
Wait, hold on. If the massive lithium-ion pack beneath the floorboards isn't what's stranding people, what is?
About 50% of the time, the actual culprit is just the mundane 12-volt battery.
You mean the exact same 12-volt battery that runs the radio in a standard gas car?
Very same one.
That is hilariously ironic.
It really is. In an EV, that little lead-acid or lithium 12-volt battery runs the computers, it runs the screens, and critically, it runs the contactors.
Okay, what are contactors?
They are physical high-voltage switches. So when you turn on an EV, the little 12-volt battery sends power to close those switches.
Okay.
And that physical connection is what links the main high-voltage pack to the motors. So if that little 12-volt battery dies, the contactors stay open. It completely bricks the vehicle. Even if you have a 90% charge in your main battery pack, you're not going anywhere.
That is incredible. You have a $50,000 piece of futuristic technology immobilized by the exact same component that killed my first sedan in high school.
Yeah, it's extremely frustrating for drivers. And the other major culprit for breakdowns is just tire issues.
Oh, because they don't have spare tires.
Exactly. Most EVs don't carry spares to save weight and maximize range. So a simple flat tire suddenly becomes a major recovery event.
But wait, when an EV is bricked, like that, you can't just call a standard tow truck, right? I mean, if you get an old school tow truck driver who hooks it up like a gas car,
Yeah.
things go very wrong.
Very wrong. You absolutely cannot use a traditional hook and chain tow truck on an EV.
Why not?
Well, most EVs don't have a true physical neutral gear that disconnects the wheels from the motors.
Right.
So if you drag the driven wheels of an electric vehicle down the highway, those permanent magnet motors act as generator.
Oh, no.
Yeah, they start producing massive amounts of electricity and pushing it backward into the inverter with nowhere to go.
So you essentially fry the electronics of the car.
Completely.
Yeah.
You can cause 5-figure damages to the drivetrain or the battery pack in a matter of miles.
That's terrifying.
It is. EVs require flatbed trucks exclusively,
Uh-huh.
and they require the driver to actually know how to navigate the touch screens to activate a specific tow mode to disengage the electronics safely.
Assuming the screen even works because the 12-volt battery might be dead.
Exactly. And on top of that, the tow operator has to use very specific tie-down points so they don't accidentally puncture the battery tray underneath.
Let me play devil's advocate for a second here.
Sure.
If these vehicles are this temperamental to recover, why are fleets and regular consumers buying them at all?
Well, because statistically speaking, EVs actually break down less often than internal combustion cars.
Really?
Yeah, the numbers sit at roughly 3.8 breakdowns per 1,000 vehicles for EVs compared to 9.4 for gas cars.
Okay, that's a big difference.
They have fewer moving parts, no oil changes, no spark plugs. But the catch is when they do fail, they fail differently.
Hmm.
The recovery is just an incredibly complex, high-stakes logistical puzzle.
And that high-stakes puzzle is exactly what created the massive market demand for a mobile solution.
Precisely.
Because if towing an EV requires specialized trucks, specialized knowledge, and carries the risk of accidentally ruining a $30,000 drivetrain, the most elegant solution is to just bypass the tow truck altogether.
Right. Don't move the car to the charger. Move the charger to the car.
Which brings us to the engineering papers from JAR. They outline the anatomy of the MECV, the Mobile Electric Charging Vehicle.
And we should clarify, we aren't talking about tossing a noisy diesel generator into the back of a pickup truck here.
Right, right.
These are highly sophisticated systems designed to safely transfer massive amounts of energy.
So JAFR breaks the architecture of an MECV down into 5 key subsystems.
Let's go through them.
The first is the Energy Storage System, or ESS. I assume this is basically just a massive block of standard lithium-ion batteries,
Yeah.
like what you'd find in the car itself.
It can be.
Yeah.
But many of the really advanced units are actually using LFP or lithium iron phosphate batteries instead.
Interesting. Why LFP specifically?
Mostly thermal stability.
Oh.
Because think about it. When you are driving a commercial van filled with high-voltage batteries over city potholes all day.
Bouncing around, yeah.
Right.
Mm.
You need a chemistry that is highly resistant to thermal runaways. So LFP batteries are slightly heavier, but they are incredibly safe. They won't easily catch fire if the van happens to get into a traffic accident.
That makes perfect sense. Okay, so the second subsystem is the power conversion unit. This seems to be where the heavy lifting of the electrical engineering happens.
It is.
These are the DC to DC converters and the inverters. But why do we even need massive converters if we are just moving power from one battery to another battery?
Because you can't just connect a wire between two high-voltage batteries like you're jump-starting a gas car.
Oh, right.
The MECV's internal battery might be sitting at 800 volts, while the stranded EV's battery is currently sitting at, say, 350 volts.
Got it.
If you dump raw mismatched voltage into the stranded car, you'll completely destroy its battery management system. So the power conversion unit actively regulates the voltage coming out of the mobile battery, so it's perfectly matched to what the receiving EV can safely absorb.
Which leads right into the third part, the charging interface. These MECVs use standardized physical connectors, right? Like Type 2 AC or CCS2 for DC fast charging.
Yep, standard plugs.
But the really fascinating part is the digital handshake. The mobile charger physically plugs in, and then it essentially has a conversation with the stranded EV's computer to negotiate the charge rate safely.
Right, they have to talk to each other. And overseeing all of that is the fourth subsystem, the control and monitoring unit.
What does that do?
These are IoT Internet of Things gateways and sensors. Tracking the thermal load in an enclosed van, pushing out 70 kilowatts of power is incredibly difficult.
I can imagine. It gets hot.
It's very hot. So these sensors monitor temperature voltage fluctuations and the overall health of the system in real time.
Wow.
And finally, all of this is housed in the fifth subsystem, the vehicle platform itself. This is the specialized commercial chassis equipped with heavy-duty fire suppression and active ventilation.
So instead of digging up sidewalks, laying miles of expensive copper wire, and begging the city for permits and utility grid studies, we are essentially building a giant, highly intelligent power bank on wheels that just drives right up to you.
That is exactly what it is.
And according to the JAFR research, building one of these MECVs costs roughly 12 to 18 lakhs in Indian rupees.
Which translates to roughly 14,000 to 21,000 US dollars, depending on how you configure it.
That's incredibly cheap compared to the alternative.
It is a fraction of the cost of a fixed DC fast charging station. Those can easily top $100,000 with all the installation and trenching.
Right.
But the real value isn't just the hardware cost, it's the speed of deployment.
Because they don't need the grid.
Exactly. These units operate completely off-grid. You can deploy a fleet of these vans in a brand new city in a matter of days, completely bypassing those 18 to 24-month utility bottlenecks.
But okay, having a technically brilliant battery van is one thing. Actually making money deploying 1,000 of them is a totally different nightmare.
Good
I
question.
mean, how are these companies surviving the logistics? Driving a heavy van full of batteries around a congested city to charge other vehicles sounds wildly inefficient on paper. You are literally burning energy just to deliver energy.
You're right. In terms of pure thermodynamic efficiency, yes, it's less efficient than a copper wire in the ground.
Yeah.
But the Commonwealth's model charging as a service isn't about thermodynamic efficiency. It is entirely about operational uptime and fleet economics.
Yeah.
And the market projections really reflect this. TechSci predicts the U.S. call market will reach over $425 million by 2030, with portable chargers alone hitting nearly $232 million by 2031.
Because they aren't just selling like a roadside rescue service for stranded
You're
consumers.
not at all.
They are selling massive B2B software solutions. Look at SparkCharge. They offer a complete turnkey fleet service using what they call Connect CMS charge management software.
Exactly. If you manage a fleet of 50 electric delivery vans, installing fixed chargers at your depot requires massive capital expenditure upfront.
Millions of dollars, probably.
Easily. SparkCharge shifts that from a capital expense to an operational expense. Their software integrates directly with the telematics of your fleet, so it monitors the state of charge of every single van in real time.
That's smart.
And they guarantee 99.9% charging uptime by automatically dispatching mobile chargers to your depot overnight to charge the vans while they're just sitting there parked.
Then you have a company like Charged EV, which is targeting a massive footprint of 1,000 units across the U.S. and Mexico. And they use a proprietary platform called PSC AI Predictive Smart Charging.
This is where the AI really transforms the whole model. Their software uses APIs to talk directly to the driver's vehicle. The algorithm factors in live traffic, the driver's current route, and their specific battery drain rate based on how they drive.
So it knows they're going to run out of battery.
It knows the battery is going to be critically low before the driver is even aware they might be stranded, and it can dispatch a mobile charger to literally intercept them.
That is wild. And they are also using this to map out and solve charging deserts, right?
Yes, they have a program for that.
Right. They call it Apex 300. They are specifically deploying mobile units to lower income or geographically isolated neighborhoods that the big fixed station networks have completely ignored.
Mostly because those areas weren't deemed profitable enough for a permanent million-dollar installation.
Right. But where the economics of mobile charging really shine is in their deployment in dense urban centers. Places like Mexico City, B-charged units down there are delivering 65 to 70 kilowatts of power in just 20 to 30 minutes.
Which is incredibly fast for a mobile unit.
And here's where it gets really interesting for the workers. If I'm an Uber driver in Mexico City, my time is literally my income.
Every minute counts.
Right. I don't make money when I'm off the clock hunting for a public charger, praying it isn't broken or blocked, and then sitting there for an hour.
Exactly.
But if the charger uses AI to hunt me down while I'm just taking a standard 30-minute lunch break, that fundamentally changes the entire economic reality of my job, doesn't it?
Changes everything. And what's fascinating here is how this trend is expanding globally.
Yeah.
Look at the consumer behavior data from TGM research on the Asia-Pacific region. They found that 33% of people in APAC use ride-hailing services weekly.
Yeah.
And 36% use food delivery weekly.
Weekly. That's a massive volume of trips.
Huge. They call it the daily convenience economy. It is driven by incredibly busy lifestyles and, strangely enough, by adverse weather.
Wait, adverse weather?
Yeah. When it rains heavily, people don't walk or take the bus. They immediately open their phones and order rides and food delivery.
Oh, sure. That makes sense.
So demand for these electric fleets spikes precisely when city traffic is at its absolute worst.
And that daily convenience economy relies entirely on these fleets maintaining absolute zero downtime.
Exactly.
Because if all the delivery mopeds and the rideshare EVs have to stop working right in the middle of a rainstorm to queue up at a centralized charging hub, the entire convenience economy just grinds to a halt.
Which is why mobile charging isn't just a luxury for these drivers anymore. It is the critical invisible infrastructure keeping the whole system moving. It transforms mobile charging from a reactive emergency roadside service into a highly proactive subscription-based utility.
It really is a total paradigm shift.
It is.
We started this whole deep dive with Thomas Edison and Nikola Tesla, who laid the groundwork for a centralized grid that was basically designed to send power in one direction.
Right, a one-way street.
A grid that is now seriously buckling under the weight of modern digital demands, extreme weather, and just aging physical wires.
But to solve the transmission bottlenecks and the psychological range anxiety and the very real towing nightmares of the EV transition innovators are just bypassing that old grid entirely.
Yeah, they are deploying off-grid mobile electric charging vehicles to close the gap.
And paired with that highly intelligent predictive countdown software, they are completely decoupling energy delivery from geography.
It's amazing. Whether you manage a corporate delivery fleet, or you drive an EV on the weekends, or you just rely on an app to get your dinner delivered on a rainy Tuesday, this mobile charging network is rapidly becoming the invisible backbone of the convenience economy you navigate daily.
Because infrastructure is no longer static. It is adapting, it's moving, and it's actively learning exactly where it needs to be.
Which leaves us with a pretty wild final thought to chew on.
What's that?
Well, think back to that glowing gas station on the side of the highway we talked about at the very beginning of the show.
Oh yeah, the permanent concrete one.
Right. Or even look at the prime urban real estate that's currently being bought up by big corporations right now to build massive fixed EV charging hubs.
Okay.
If energy delivery becomes entirely mobile, entirely predictive, and completely untethered from fixed locations, what happens to all that real estate?
That's a really good question.
In a decade or two, are those prime corner lots just going to become obsolete monuments to a past era? Are we going to look at gas stations the way we look at old phone booths? It is definitely something to ponder the next time you plug in.